Dear students, today we are going to discuss about the laser rate equations. The rate equations govern the rate at which populations of various levels change under the action of a pump and in the presence of the laser radiations. The rate equations provides a convenient means of studying the time dependence of the atomic populations of various levels under the presence of radiations, frequencies corresponding to different transitions of the atom. It also gives the steady-state population difference between the actual levels involved in the laser transitions, and it helps us to study whether an inversion of population is achievable in a transition, and if so, what would be the minimum pumping rate required to maintain a steady population inversion for continuous wave operation of the laser. As we all know that population inversion cannot take place in a two-level laser system. A minimum pump power is required to obtain population inversion in a three-level laser system. A similar treatment will show that the attainment of population inversion in a four-level laser system is not dependent on pump power. So first of all, we shall begin with a three-level laser system. Here we consider a three-level system consisting of energy levels E1, E2 and E3. Here the population of E1 is N1, population of E2 is N2 and population of E3 is N3. And we assume that only these three levels are populated and that the transition takes place only between these three levels. For such a case, the total number of atoms per unit volume N equals N1 plus N2 plus N3. Here the pump is applied for the transition from level 1 to 3. That is, pump lifts the atoms from level 1 into the level 3, from which they decay rapidly to level 2 through some non-radiative process. That is, here the level is metastable and the lasing transition is from level level 2 to 1. So we can say that the pump effectively transfers atoms from level 1 to level 2 through level 3. If the relaxation from level 3 to level 2 is very fast, then most of the atoms in the level 3 will relax down to level 2 rather than to level 1. Level 3 can be a broad level since that level is not one of the laser levels. Hence, a broadband light source can be used effectively as a pumping source. The ground level is the lower laser level. That is, more than 50% of the atoms from level 1 have to be lifted up to population inversion between levels 2 and 1. Here the change in population of level 3 is described as N3 by dt equals Wp into N1 minus N2 minus N3 T32. It's obtained as follows: N3 by dt equals N1 Wp minus N3 Wp minus N3 T32. And On simplifying, we get it as dn3 by dt equals Wp n1 minus n3 minus n3 T32. Here, n1 Wp represents the number of induced absorptions per unit time. Here, n1 Wp represents the number of induced absorptions per unit time, which results in the 1 to 3 transition. Similarly, here N1 Wp, it represents the number of induced absorptions per unit volume. One represents the number of induced absorptions per unit time per unit volume, which results in the 1 to 3 transition. Here N3 Wp represents the number of stimulated emissions per unit time per unit volume in the transition 3 to 1. The term N3 T32, it represents the transition 3 to 2, and it is caused mainly by a non-radiative process. So we can write T32 equals A32 plus S32. Here A32 represents the Einstein coefficient A corresponding to a radiative transition connecting levels 3 and 2. Here S32 represents the non-radiative transition from level 3 to level 2. From level 3, similarly we can write the rate of change of population of level 2 equals dn2 by dt, it is equal to Wi n1 minus n2 plus Wi n1 minus n2 Wi n1 minus n2 plus n3 T32 minus n2 T21. Here term represents the stimulated transition between the levels 1 and 2. The second term, it represents the spontaneous transition from level 2 to level 1. The second term represents the spontaneous transition from level 3 to level 2, and the third term represents the spontaneous transition from level 2 to 1. Here Wi is proportional to Einstein coefficient B21 and to the energy density associated with the lacing transition from level 2 to 1. Also T21 represents the net spontaneous relaxation rate from level 2 to 1. And if this transition rate is predominantly radiative, then we can write T21 nearly equal to A21, where A21 represents the Einstein coefficient. Similarly, we can write dn1 by dt equals Wp n3 minus n1 plus Wi n2 minus n1 plus n2 T21. Here, the first two terms First two terms represent the stimulated transitions between levels 1 and 3 and levels 1 and 2 respectively, and the last term represents the spontaneous transition from level 2 to level 1. Also, we can write the n1 by dt plus dn2 by dt plus dn3 by dt equals 0. So here we can see equations. Equation 2, 4 and 5 are called as the rate equation, and it gives the rate of change of population of the three levels in a three-level laser system in terms of WP and WI. At steady state, we can set the time derivatives to 0 and then solve this equation and find the values of n1, n2 and n3. And on further simplification, we get n3 equals WP divided by WP plus T3 to n1. And on simplifying equation 4 and substituting dn2 by dt equals 0, we get n2 equals Wi plus T32 WP by WP plus T32 into n1 by Wi plus T21. Again, from equation 1, 7 and 8, we obtain the expression for population difference between the levels 2 and 1 as n2 minus n1 by n equals WP T32 minus T21 minus T32 T21 by 3 into WP Wi plus 2 WP T21 plus 2 T32 Wi plus T32 WP plus T32 T21. From equation 9, we can say that in order to obtain population inversion between levels 2 and 1, that is for n2 minus n1 to be positive, the necessary condition is that T32 greater than T21. So according to equation 10, we can say that the lifetime of level 3 must be at least smaller than the lifetime of level 2 for the attainment of population inversion. And in order to achieve population inversion, a minimum pump power is also required, and we can write it as WPT equals T32 T21 by T32 minus T21. And for obtaining population inversion, WP should be greater than WPT. So this is a necessary condition for obtaining population inversion, that is WP must be greater than WPT. Also, we know that T21 equals A21. So the expression for WPT can be written as WPT equals, instead of T21, we can substitute A21, that is T32 A21 divided by T32 minus A21. And therefore we can say that for obtaining population inversion, WP must be greater than WPT, as T32 very much greater than A21. Therefore we can write WPT equals T32 A21 divided by T32, which is equal to A21. That is, we can write WPT equals A21, that is spontaneous emission 3 to 1 is greater than the spontaneous emission 2 to 1. So then for population inversion to occur, we know that WP should be greater than WPT. That is WP should be very much greater than T21, which is nearly equal to A21, which is equal to 1 by tau SP. If power at the laser transition frequency is very high, then from equation 9 we can write N2 minus N1 by N equals, or it is nearly equal to WP T32 minus T32 T21 by WI into 3 WP plus 2 T32. So if you follow this approximation, we can say that the population inversion is inversely proportional to Wi. N minus delta n by 2 into WP equals n plus delta n by 2 into T21. Here delta n equals n2 minus n1. Here delta n equals n2 minus n1. Thus for a 3-level laser system, we can write capital N equals n1 plus n2 plus n3, which is nearly equal to n1 plus n2. Here we have assumed that the atoms from level 3 drop down to level 2 so quickly that level 3 is essentially unpopulated. Then we can write n minus delta n by 2 nearly equal to n1 and n plus delta n by 2 nearly equal to n2. So here the LHS of equation 14 represent the number of atoms per unit volume in level 1 lifted to level 2 per unit time, and the RHS of this equation represent the number of atoms per unit volume decaying spontaneously to level 1. So from equation 12 it is written that N2 minus N1 by N equals WP minus T21 by WP plus T21. Since for a 3-level laser system that the atoms from level 3 drop down to level 2 so quickly that the level 3 is essentially unpopulated, which means N3 nearly equal to 0. Therefore, we can write that the equation N1 plus N2 plus N3 equals N. It becomes N1 plus N2 equals N. Make the threshold pumping power required to start laser oscillation. Here, the number of atoms pumped per unit volume per unit time from level 1 to 3 is WPN1. Let the pump frequency be nu P. Then the power required per unit volume will be P equals WPN1 H nu P. Therefore, the threshold pump power can be written as P threshold equals WPT N1 H nu P. And WPT equals A21. Therefore, PTH equals A21 N1 H nu P. N nearly equal to N1 plus N2 and N very much greater than N2 minus N1, then we can assume that N1 equals N2, which is nearly equal to N by 2. Therefore, P threshold PTH equals A21 n by 2 h nu p or pth equals n by 2 h nu p by tau sp, where we have written A21 equals 1 by tau sp.